Right. So then I'm happy to introduce Cody Stockdale from Clemson University, and he's going to speak about compact pseudodifferential and Fourier integral operators via localization.
Okay, thank you. Thank you for the introduction and invitation, and thank you all for being here and your attention. So I want to talk about sort of an application of a general idea that we've seen applied in a few different situations. So the idea here is we want to consider compactness of operators, compactness and boundedness of certain operators on their natural spaces. And we're going to do this in sort of like a frame theoretic approach. So the idea is if you have an operator and a particular frame for the space that you care about its properties on, a frame that kind of plays nicely with your operator in some sense. So there's going to be some sort of invariance with respect to this frame. Then what we're going to observe is that the boundedness of this operator corresponds to the corresponding matrix being almost diagonalized with respect to this frame, and the compactness um, is going to correspond to, compactness is a stronger property than boundedness. So we should have our operator, the operator's matrix representation being almost diagonalized with respect to our particular frame. But more than that, we're going to ask for some sort of decay in the direction of the diagonal of this matrix. So that's the general idea at a very high level. We've kind of applied this and investigated in a few different situations. Most recently in a joint work with Mishko Mitkovsky in the harmonic, kind of like a classical harmonic analysis area of studying compactness of Calderon-Zygmund singular integral operators. We've also applied this in a few other places with Toeplitz operators on Bergman spaces, a sort of complex analytic type of framework in a joint work with Mishko Mitkovsky, Brett Wick, and Nathan Wagner. What I want to talk about is another application of this sort of general philosophy in a more time frequency analysis realm for pseudodifferential and Fourier integral operators. And this is a particular paper that's a joint work with my former undergraduate student, Cody Waters. So I want to give him credit for this. He is now working on his PhD at Washington University in St. Louis. Okay, so what are the operators that we care about here? So we're going to start by introducing the Cohn-Nierenberg pseudodifferential operator, which we'll denote by this op kn of its symbol sigma. It's given by this formula where you first take your input function f, you take its Fourier transform, you multiply that by this symbol function sigma of both the time variable and the frequency variable, and then like take the inverse Fourier transform. So if sigma is just a constant function, just sigma of x equals 1 always, then this operator is just going to be the identity. Um, but more generally, if sigma is like a polynomial and the independent variable c, then this recovers the differential operators, the spatial derivatives. More generally, if sigma is just a function of the frequency variable and doesn't depend on x, then this enters into the study of Fourier multipliers. So there's a whole theory of Ormander and Marcinkiewicz and Michelin that are studying these types of operators. But more generally, we want to have general symbols that could depend both on the frequency variable and this time spatial variable. Um, More generally than this formula that I had up top, that just depends on x here, I could unravel this Fourier transform of f. I could actually write it out in terms of what it is as its integral definition of the Fourier transform. So then this would be expressed as a double integral with with variables y and c. Um, and I could more generally have this type of expression if I unravel that definition of the Fourier transform, pull the integral out front. And if I take this quantity here and plug in tau equals to 1, so this part here would go away. That would be a 0, and there wouldn't be any dependence on y. You just have dependence on x. That would reproduce exactly the formula we have up top. But also in like the math, physics, and time frequency analysis communities, often it's necessary to look at the case where tau equals to a half. So this dependence here would be the arithmetic mean of x and y. And this is what's called the Weil pseudo-differential operator. So those are sort of our starting points, the main objects that we're looking at. And we'll go to some higher generality uh, later just to see how far this theory can be pushed. Okay, so classical results on this. I guess the most famous classical result is Calderon and Vaillancourt's paper in the Proceedings of the National Academy of Science from 1972. And loosely it says, well, it says that if sigma, their symbol, is has bounded derivatives, so it needs to have some amount of smoothness, and these derivatives should, not blow up. If it has bounded derivatives up to some certain finite order, I think it's like just, twice the dimension, maybe plus one, some sort of dimensional constant, then the associated pseudo-differential operator will be bounded on L2. Okay. In this work, they maybe weren't exactly, I mean, they do have quantitative bounds on the number of derivatives you need, the amount of smoothness. But more recently, or sometime after this, the community was interested in understanding how much smoothness the symbol needs in order for the associated operator to be bounded. And that was described in this paper of Heil, Ramanathan, and Tapuwala of 1997, um, where they said that if S is just any number that's bigger than twice the dimension, and sigma is in this Holder-Lipschitz space, lambda S, then the associated pseudo-differential operator is going to be bounded on L2. So you're kind of quantifying that number, the amount of derivatives you need, the amount of smoothness you need, to just being slightly bigger than 2 to the n. And this is sharp in the sense that if you say S equals to 2 to the n, then there are examples of pseudo-differential operators that would fail to be bounded. So in this realm of this kind of classical um, Lipschitz conditions on your symbol, this is the best that you can do. Independently, in a sort of different area with different motivation, Sjöstrand in 1994 gave a different formulation on the symbol, condition on the symbol that would guarantee the boundedness of the associated operator. So if sigma is in this class, which we denote by m infinity 1, which is commonly called the Sjöstrand class, uh, because of this result here. This is an instance of what's called a modulation space, which I'll describe in a couple slides. That condition is also sufficient for the boundedness of the operator on L2. Okay, and it turns out that any symbol that's in lambda s for s bigger than 2n is also going to be in m infinity 1. So we're weakening the hypothesis. This is a weaker hypothesis that still gives you the boundedness on L2. And it's somehow, in some technical senses, the correct hypothesis. You kind of can't do better in certain senses. So summing this up in Groschenig's work in his book on time frequency analysis from 2001, we have this general result, which we're going to take as one of our motivating results for boundedness of pseudo-differential operators. It says if we have two parameters, p and q, bigger than or equal to 1, smaller than infinity, and tau is any number between 0 and 1 corresponding to our tau pseudo-differential operator. So this includes the Kohn-Nirenberg and the Weil pseudo-differential operators. If your symbol is in the Sjöstrand class, m infinity 1, then your operator is going to be bounded not only on L2, but on any modulation space MPQ. Again, I'm just kind of wanted to state the theorems here at the beginning, but I'll define some of this more technical notations here in a couple slides. So some comments. This Holder-Lipschitz space lambda s is properly contained in m infinity 1. So our hypothesis here is relaxed. And M22 is actually going to be equal to L2. So more generally, we have bounds on any MPQ, in particular taking P equals Q equals to 2, then we recover the boundedness on L2. So this result here is the most general version of everything above. Loosely, the modulation spaces MPQ are saying that your function should be in LP and its Fourier transform should be in LQ. So with that idea by Parseval's identity, it's kind of clear to see that M22 is the same thing as L2. Okay, so that's what we understand about boundedness of these operators on the natural spaces, these modulation spaces. The compactness is we should ask for a stronger property on the symbol, not just that's in this m infinity 1, but we should ask for some sort of vanishing. In this case, the natural thing to look at is the vanishing of the symbol's what's called the short time Fourier transform, which we denote by this v sub phi of sigma. So the result here that we're going to take as our motivation is a result of Benyi, Groschenegg, Heil, and Okuju from 2005. Same hypotheses that we had in the previous theorem, PQ between 1 and infinity, tau is one of these parameters. and sigma is an M infinity 1. So we know from the previous result that the operator is going to be bounded on MPQ. But if additionally this short time Fourier transform vanishes as the inputs go to infinity, then that's going to guarantee the compactness of the operator on MPQ. And I'll define the short time Fourier transform again here in a second. But this is the main idea. A condition that gives you boundedness, an additional vanishing condition that will guarantee the compactness. And our goal here is to unify these results with what we call a condition that we call localization of the operator. It's going to depend on some matrix coefficients with respect to a particular frame. We want to unify and push these to higher generality. We'll talk about how this can extend to, for example, weighted modulation spaces, and we'll talk about more general pseudodifferential operators that are not of just of this form op tau. And we'll kind of give an overall theorem that can address multiple different situations at the same time. So kind of unifying and extending these two results is the goal. Okay, so yeah, basically just writing down what I said out loud. We want to recognize this as a particular instance of a more general phenomenon. So our main result, I know this is technical, but um, let's just kind of ignore some of this technical notation. But the result says that if you have P and Q bigger than or equal to 1, smaller than infinity, just as before, G1 and G2 are just like some general window. Think of G1 being the same thing as G2 being just the Gaussian e to the minus x squared absolute value. Um, Chi be a bi-Lipschitz diffeomorphism. That's a technical thing that we need to include in order to address general Fourier integral operators. For the pseudo-differential operator discussion, just imagine that this function chi is just the identity. So imagine that's just the identity. Nu is an admissible weight. I'll tell you what admissible means. Again, you can just imagine nu as a constant function. The unweighted case has all the content here. I just wanted to present the results in their more general form that we can handle. But basically, our result says that if you have an operator that is localized, I'll define this, that is localized, which says that its matrix coefficients are concentrated along the diagonal, then that operator is going to be bounded on the modulation space. We call this one a pullback modulation space, but if chi is the identity, then it's going to be just the same thing as MPQ, MPQM, this weighted modulation space. If additionally your operator satisfies some weak compactness condition, which encodes some decay in the direction of the diagonal of the matrix representation of your operator, then that would guarantee that T is compact between these same and corresponding spaces. So we ask for something a little bit more property of our operator that we can guarantee through its symbol, and that should give us the compactness. Okay, so this result already we can see contains the previous motivating theorems A and B. If you take G1 and G2 to just be the Gaussian window, e to the minus, like a normalized e to the minus absolute value x squared, chi being the identity, the weights just being 1. Because this condition, sigma and M infinity 1, implies that op tau is localized. That was another result of Groschenig from, I believe, 2006. And then we show that the vanishing of its symbols for a short-time Fourier transform will imply this weak compactness condition. So this already recovers the previous results, but what else can this say? Can we apply this type of framework, this perspective to understand more general pseudodifferential operators or handle these weighted spaces or also Fourier integral operators? That's sort of the idea. Okay, I already took up most of my time just talking about the background in the first few slides. That's okay. The main idea is more important than all the technical stuff. But let's go through that. And this is what I was saying out loud. The localization quantifies the idea that the matrix coefficients, with respect to, in this case, from our time frequency analysis perspective, we're going to use the Gabor frame. It should be concentrated on diagonal. That's what localization is telling us. And the weak compactness condition asserts that these coefficients decay in the direction of the diagonal. That's the main key takeaway that we've seen being applied in other areas, in this case, in this pseudo-differential operator area. Okay, so I want to describe what are the modulation spaces, what are the short-time Fourier transform. The first thing I need to define is this time frequency shift. So we'll take a parameter in the phase space. So x is like a spatial variable, c is a frequency variable, and we take a translation in x and a modulation in c. When we take this composition, we call that a time frequency shift. We're shifting both in time, aka space, and also in the frequency domains. This space here is a technical thing. These are just a space of test functions that we need in order to define our spaces, and we're assuming that when we integrate, um, we take f and we pair it with the time frequency shift of this Gaussian, and that should be integrable in both variables x and c, integrable with respect to this weight function. So we need to get like a little bit of extra decay, enough to kill off this exponential. Um, Again, this is a technical thing, but we should just imagine our standard test function being a Gaussian itself. So imagine whenever I say like G1 or G2 is in this S theta, just imagine that that G1 or G2 is a Gaussian. Okay. With this definition, we can define the short time Fourier transform. So what you do is you take a function f, say it's defined on Rn, or it's technically a tempered distribution of these test functions. Um, and what we do is we pair it with a time frequency shift of a particular test function. In practice, G is going to be a Gaussian window. We take time frequency shifts of this. Now it's going to be a function of two variables of R2n, um, and take this ordinary L2 pairing. Okay, so this sort of encodes both spatial information and frequency information of your function at the same exact time. Um, and with this, if I consider these shifts, the time frequency shifts of the Gaussian at all spatial components and all frequency components, this collection of functions forms a continuous Parseval frame for L2, in the sense that the L2 norms can be given as integrals of these short time Fourier transforms. This is telling us that we have a frame, essentially like a continuous type of orthonormal basis in some sense, um, for our space L2. And with respect to this frame, we'll see that our operators are in some sense invariant under conjugation. Um, and that's going to allow us to prove our estimates and our main results. More generally, we can have an actual representation interpreted weakly with this stuff. Okay, there are some conditions on the weights that make this work. So they should be even in each coordinate, which have a submultiplicative property. And this is this Gelfand-Rykov-Shilov uh, condition that basically says that your weights don't grow too fast. They can grow at most like exponential, or no worse than that. Um, Anyways, okay, so I don't want to get into the technical reasons why we need to get in these conditions on our weights, but we can define these mixed Lebesgue spaces, these weighted mixed Lebesgue spaces. So if we have a function of two variables of time and of frequency, we can first take an LP norm in the spatial variable, and then afterwards take an LQ norm in a frequency variable. And I have this more general function M here just to get a weight, but in this talk, let's just imagine that M is equal to 1, so we don't have to worry about it. We'll omit that notation when P is equal to Q or when M is equal to 1. So we have these mixed Lebesgue spaces that we can take a functions of multiple variables, and then we can define our modulation spaces. More generally, we can define these pullback modulation spaces. But the idea here is we should take chi. Imagine that chi is just the identity, so its inverse is the same, and I don't need to write this. This composition would go away. What I want to do is take the short time Fourier transform, which will take a function of just a single variable, raise it up to a function of two variables, one in the time domain and one in the frequency domain. And I want to say that that is in the LPQ. When I take this short time Fourier transform, that should be in this mixed LPQ space. We can take it with this by Lipschitz diffeomorphism if we want. And we can take weighted versions as well, but that's the idea. The short time Fourier transform should be in this mixed LPQ. That defines our modulation spaces. This is a Banach space. It's independent of the choice of window. We have some continuous embeddings, and these test functions are going to be dense in the space, so we can kind of reduce to studying those. And um, in certain situations, we can relate these pullback modulation spaces to just ordinary weighted modulation spaces where the weight is composition with our function chi. Again, technical things, but the important thing here is just the definition of the modulation space. And I know I'm already short on time, so I'll just kind of go through quickly the next couple slides. This localization condition, this is what we mean for an operator to be localized. So we look at its matrix coefficients. I take T and I apply it to a time frequency shift of some test function, and I pair that with another time frequency shift of a test function. So this is essentially um, we're taking our Gaussian window. Imagine G1 and G2 are both a Gaussian window, and this is a Gabor frame. We basically take T, apply it to an element of the Gabor frame, and pair it with another element of the Gabor frame, and saying that that should be bounded above by some integrable function. L is going to be an L1, some integrable function of the difference of these parameters Z and W. So basically it's saying that if Z and W are close together, then this is allowed to have content, allowed to have mass. But as Z and W get far away, then this quantity here should get small enough so that it's bounded above by an integrable function. So it can only be not small when Z and W are close. As Z and W get far away, these coefficients should get small. So it's concentrated on the diagonal. And our weak compactness condition also, we look at these matrix coefficients, ignore the chi for the moment. That's a technical thing to handle certain generality. But saying that these, um, if Z and W are somehow close together, so W is going to be in some Z translate of a compact set K, these matrix coefficients, as we take Z going far away, so W is also going to be close to it. They're both going far away from the origin. So this is like the direction of the diagonal. We should get to K. This whole quantity should go to 0. Okay, so that's how we quantify those. And this is a restatement of our main theorem. The proof of the boundedness is a pretty easy, like, just one paragraph or so. Just does the reproducing formula of the frame, the localization hypothesis, and we apply Young's inequality for convolution for mixed Lebesgue spaces. The compactness is a little bit more interesting, and it requires verifying a Rees-Kolmogorov type theorem, which we have from this paper of Dorfer, Feistinger, and Groschenig, which they say that a set in the modulation space is precompact if and only if we look at the tails of the short time Fourier transform integrals in LPQ. We know that they all have to be, that this has to be for each one of these f's, this tail should go to 0, but we're saying that should go to 0 uniformly over all f in that bounded set. And that's what guarantees the compactness, and that's what we verify. Okay, so to apply this to the tau pseudodifferential operators, we can actually see if our symbol is in this type of modulation space, this weighted modulation space, Stoichstrian class M infinity 1, more general than our hypothesis from our motivating theorem, and a short time Fourier transform decays, then it's compact. So that recovers our previous theorem. And how we get this is this decay, this short time Fourier transform implies this condition here, which is stronger than our weak compactness condition. So symbol short time Fourier transform decay implies weak compactness, which gives us the compactness from our previous theorem. We can also do this with symbols in this Wiener amalgam space. And we appeal to some other literature of Cordero, Nicola, and Trapasso from 2019, where they gave localization for like the almost diagonalization, the localization for this operator with such symbols, and then we can apply the same scheme to get its compactness. The more interesting part of our paper is that we can also extend this to handle 3-parameter pseudodifferential operators. So if you remember our op tau at the beginning, our symbol was a function where we took like this convex combination of x and y. In this situation, we're here allowing sigma to be a function of 3 variables where x and y can interact completely independently. This is actually the generality that Calderon and Valancourt originally did in their paper in the early 70s. And we, again, in this case, can see that if sigma is in a Stoichstrian class, M infinity 1 now of 3 variables, then T sigma is going to be bounded. And if it has this sort of decay condition, where we get vanishing of the symbol, translates in the spatial variables and the frequency variable, then we get compactness. This condition here looks a little bit different than what we had before. But I want to justify that that's okay, because if we took this condition here and just applied it in 2 variables, that we have this decay in this distribution sense, that's actually equivalent to the decay of the short time Fourier transform. So we have these 2 equivalent conditions, and this one on the right is what we generalize to the 3-parameter setting. This one requires a little bit more work. So what we do to prove that is we take our symbol and we decompose it into these symbols we call sigma k, where they're Fourier supported in some translative compact set. And we call this an atomic decomposition. It's like a decomposition of our 3-parameter pseudo-differential operator into this countable sum of kind of easier, in some other sense, localized operators. So what we do is we handle each of these pieces directly, show that the operators with atomic symbols are nu localized. And at the vanishing of the translates of the atomic symbol at the Sigma k implies the weak compactness. And then we lift that to the general T sigma through this proposition up top. Then we can apply our main result. Fourier integrals is our other setting. And I'll end just here very quickly after this. Um, our last application. So here we're taking our symbol just as we did in the Cohn-Nierenberg setting. So it just depends only on x and c. Take the Fourier transform. What we're changing here is the phase when we like invert the Fourier transform. So instead of just having x dot c here, we have a general phase of phi of x comma c. So it's more general in that situation. There are natural phases, which we call tame phases, that are adapted to this, that make this theory work for such operators that are natural for their applications. And how we can relate these phases to the classical setting is through this canonical transform. That's where our function chi comes from, where we have to deal with this pullback modulation space business. And we get a theorem as well that says if we have a symbol that's an M∞1 in the setting, then we get boundedness on the modulation spaces. If additionally the symbol has vanishing short time Fourier transform, then we get compactness. The thing here is that we need to have our input space be M, this pullback modulation space, MPQ of M comma chi. The same thing down here for the compactness. This result compares to earlier work of Cordero, Nicole, and Rodino, where they investigate unweighted boundedness in a diagonal situation when P is equal to Q. So we handle weights and the off diagonal when P is equal to Q, or P is not equal to Q. Okay, and in general, if you take P not equal to Q, then you don't get boundedness on the modulation spaces. And that's why we actually invent this definition of pullback modulation spaces. And Fernandez, Galvez, and Primo in 2019 have a paper where they talk about compactness, again, in the P equals Q case. And what we are able to do is to recover these results and give a replacement in the P not equal to Q situation. Our theorem, again, follows by the vanishing of the short time Fourier transform, gives us a condition like this, which would imply the weak compactness condition. And then we have the localization, again, from a different result of the same three authors, or actually Groschnig is this other author. And I get the weak compactness when we apply the main theorem. Okay, so I apologize for going a little bit over time, but thank you for your attention.
Thank you very much. And I think that's perfectly fine. We just have to shorten question time. So let me stop recording.